Welcome to Brain Vision.
So here's our cube, and we want to find the mass of the air inside of it. Well, we need to find the volume first, right? And the volume of a cube, 10 centimeters per side, is just going to be, 0.10 meters, because we want to convert this to meters cubed. That's going to be meters cubed. So to find the mass of the air in there, we need to find how many moles of air there are in this cube. If we can do that using the ideal gas law, PV equals nRT. We can plug in numbers. Pressure 1.01 times 10 to the 5 pascals times our volume, which is 0.10 cubed, is equal to number of moles, and times R, 8.31, times our temperature, 300 Kelvin. Solve for N and find that we have 4.05 times 10 to the negative 2 moles. And now return to our molar mass M, which is 28.9 grams per mole. And we can just multiply our molar mass by our number of moles, 4.05 to 10 to the negative 2 moles. And this will, of course, give us a mass, M, which is equal to 1.17 grams, or 1.17 times 10 to the negative 3 kilograms. Now in part B, we want to find the gravitational force, which is just mg, right? And we can plug in our mass, 1.17 times 10 to the negative 3 kilograms times g, 9.8. And we should get a gravitational force equal to about 1.15 times 10 to the negative 2 newtons. Now part C asks us, okay, what about the force that the gas exerts on each face of the cube? Well, this is related to pressure with the equation F is equal to pressure times area. We know that the area of one side of the cube is equal to 0.10 squared. So we can just plug in numbers. Our pressure, remember, is 1.01 times 10 to the 5 pascals. That's just the standard atmospheric pressure. Times our area, 0.10 squared. And our force exerted on each face is going to be equal to 1.01 times 10 to the 3 newtons. Now, finally, we wonder, okay, why is the force exerted on our face so much larger than the gravitational force? Well, it's because inside of our cube, I wonder if I can go back to my cube drawing here. We know that each one of these particles is kind of moving, right? And they're actually moving quite fast, and we can find that speed with through other formulas. VRMS comes to mind for me, but you wouldn't have to worry about that for this question. But essentially, these speeds and the force and energy in each one of these particles or molecules is much greater than the force that gravity has on all of them. And remember, there are going to be so many of these particles. I mean, we're talking in the order of like 10 to the 20, 21 for this question amount of a molecule. So thinking of how many of them there are moving so fast, it makes sense that it's so much greater than the force of gravity. To make this super explicit is because, again, they're just the speeds of these molecules is very large.